Okay, hello everyone. Today I'm going to be talking about pipelining, hazards, and also a little bit about FSMs. So let's get started with FSMs. FSM. Okay, so what is an FSM? A finite state machine, not a free speech movement. It's definitely not a cafe. Okay, that's number one. What it is, it's a graph. It's a graph that describes hardware, and in this graph, there are vertices, right? And these vertices are states. They're states that our program or our hardware can be in. And we have edges going between the states. And in fact, each state has two outgoing edges. The first of these edges is if the input is 1. And the second is if the input is 0. So an example is the one in 1.1 on your worksheet. So in this example, there's a vertex or a state 0, and there's another vertex 1. And you start off at 0, and each of these vertices has two outgoing edges, like I said. So 0 has an outgoing edge that leads back to itself, marked 0/0. And it has an outgoing edge to 1, marked 1/0. Okay. And 1 has two outgoing edges, 1 to 0, marked 0/0, and 1 to itself, marked 1/1. And the idea here is that, let's look at this edge, for example. This edge, there's a 0/0, and that means on input 0, output 0, and go back to state 0. So as you can see on each edge, three things happen, right? First, some input happens which prompts that edge prompts the graph to traverse that edge, and then the graph outputs something and goes to a new state. So in this case, if you start off at vertex 0 and you see the input 0, you're going to go back to vertex 0 on that edge and output 0. So what if you see input 1 at state 0? Well, if you see input 1, then you'll go to on this edge, right? Because this edge has a 1, which corresponds to the input 1. So you'll traverse here, which means you'll output 0, and you'll end up at a new state. You'll end up at state 1. So at every single time step, you can think of you going to a new state on this graph based on some input. So you either get input 0 or 1, and depending on what that input is, you go to a new state, and you will output something. And these FSMs can be used to describe a lot of interactions between circuit elements. Right. So let's see what this FSM does, because that's what the question is asking. So you'll notice that if you start off at 0, you keep getting zeros, you'll just keep going in circles, right? You'll never leave 0. If you get a 1, however, you get a million zeros. If you get a 1, you'll end up over here at this state called 1, right? So maybe it was named that way on purpose. But if you get a 0 at this point, you'll just go back to 0, right? And then you keep getting zeros, you just keep going forever. What's really interesting is where this graph outputs a 1. And it only outputs a 1 when you're already at the state 1 and you get another 1, right? But then every 1 you get, you'll output another 1, and another 1, and another 1, and another 1, and oh, we got a 0, so now we're back at 0. And we got a 1, but we didn't output 1. We had to be at 1 and then get another 1 to output a 1. So if you look at this graph, you'll notice that what it really does is it outputs a 1 whenever there's at least 2 1s in a row. Okay? So we can sort of prove that with an example. Let me just write this down. Outputs 1 if there are at least 2 1s in a row. So the example that the discussion gives us is this 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0. It's just, what is this output? Well, given this rule here, the output's 1 if there are at least 2 1s in a row, I'm sure that you'd guess that it would do this: 0, 0. Oh, now there's two ones in a row: 0, 0, 0, 0, 0, 0, 1, 1, 0, right? And notice we didn't output a 1 here because there's only one 1. And we didn't output a 1 here because there's only one 1. But once we got here, now there's been two 1s, so now we can output a 1. And same thing happened here, right? And the reason we outputted two 1s is because on both of these ones, there was a 1 right before it. So there was at least two 1s in a row. Let's just verify that this is what happens. So we start off at 0, right? This is our start. And then we get a 1, right? Which takes us here. And we haven't outputted anything yet, right? But then we get another 1, right? And that takes us back into the loop, self loop. And now we've outputted a 1, which is exactly what we expected. We end up back at 0, right? We go get another 0. We go back to 1, and we get another 0. And then we get another 0. And this whole time we haven't outputted a single 1, which is exactly what we expected, right? Then we go back to 1. Once we're back at 1, we get two more 1s in a row, which causes us to go in this loop two more times. So you can see that this FSM does exactly what we expected. Okay, cool. So now let's go on to 1.2 to a harder FSM. That was a little too easy for you. So 1.2 asks you to fill in the FSM. So it gives you these three vertices, start, 1, and 2, and it says fill in an FSM that will output 1 whenever we have two repeating bits. So output 1 if there are two repeating bits, and 0 otherwise. So a lot of the time these FSMs are labeled in a way where the states make sense. So actually, this is a typo. In the discussion, there's a 0 here. So that makes more sense. Because remember in the last FSM, we saw that sort of this state over here sort of corresponded to if you just seen a 0. And this state corresponds to if you just seen a 1. You're always at this state if you just seen a 1. You're always at the other state if you just seen a 0. And we can sort of guess that that's how this is going to work as well. That's how these things tend to work. So we have a starting vertex this time instead of a starting like arrow that points at a vertex. It's all right. You can name vertices whatever you want in FSMs. So you could even go back to the start if you wanted. But anyway, so let's say we start off here and we get a 0 or a 1. Well, if we get a 0, then we can go to the state called 0, right? And if we get a 1, we can go to the state called 1. But either way, we shouldn't output anything because we don't have two repeating bits yet. We only have one bit. So let's mark this. And on input 0, go to state 0 and output 0. And on input 1, go to state 1 and output 0. Okay, cool. Now let's say we're at state 1, right? Because we've seen a 1. Well then, if we see another 1, then we should output 1, right? That's what we want. And we should go back to 1. And the reason we should go back to 1 is in the case where we have 3 1s in a row, for example, you would want to output a 1 here, but we would want to output another 1 here because there are, in fact, two repeating bits both here and here. So we want to always go back to the 1 so that we can make sure that this behavior actually happens, right? And the same thing should happen here at the 0. So we should just go back to 0 on input 0 with output 1. Okay, cool. So now we're just missing two more edges. I know we're missing two more edges because each vertex has to have two outgoing edges. So this vertex, the start vertex, has two outgoing edges, but the 0 and 1 vertices are missing edges. So we probably need to deal with a situation where you've seen a 1 and you need and you see a 0 right after. What do you do? Well, if you see a 1 and you see a 0 right after, that's not a repeating vertex. I mean, that's not a repeating bit. So you really should not output a 1, right? And we said that this vertex right here, 0, sort of corresponds to when you've seen a 0. So let's just sort of draw this arrow here from 1 to 0 and say on input 0, you should output 0 and go to 0. Because we need to add the backwards edge, right? So on this backwards edge, if you get a 1, you'll output 0. And that's the end of our FSM. And you can try this out on some inputs. I won't, but you should trust me because I was hired, I guess. That's the reason you should trust me. Okay. 1.3. So 1.3 is tougher. That's how these worksheets go, I guess. And 1.3 asks you to output a 1 if you see a pattern that looks like this. There's going to be 1, 1, and and then there's going to be a bunch of zeros, right? Or at least 1 0. And then there's going to be 1 1. So if you see a pattern that looks like this, then you should output a 1. So let's draw the diagram for this. So you'll start off, once again, as starting vertex. And let's do the thing we were doing last time, where we had a 0 vertex and a 1 vertex. Okay. So if we see a 0 vertex, we can't even start, right? The pattern has not even started. So in this case, right, we definitely should output a 1, but 0 shouldn't really lead anywhere in our FSM, if that makes any sense. 0 is kind of like a reset. Okay. Let's say you get a 1, okay? If you get a 1, you also should not output anything yet, because you should only output a 1 once you see this entire pattern. So let's say, let's go back to 0. So let's say you got a 0 on your first bit. Let's say you get another 0. Well, in that case, you still haven't progressed at all, right? So I think it makes sense to just go back to 0 in that case. Well, what if you get a 1? If you see a 1, then this pattern has started, right? So we can go over here. So this is a really good start. If you get zeros, you'll just stay looping in 0 forever until you get a 1. And once you get a 1, that means the pattern has started, right? And now what you want is you want another 0. So if I get another 0, maybe I should loop back here. But then I realize that I'm kind of dead-ending myself, because even though this is sort of the 0 state, right? This 0 is sort of the loser 0, right? So this is the 0 before you hit a 1. And what that means is that we sort of want to separate this out from the winner zeros, or the zeros after you've hit a 1, because those are different. We don't want to just go back to the old 0, because then we're stuck to just getting zeros over and over again, or getting a 1, and that means we started our sequence. But getting a 1 after getting the middle zeros actually means we should have finished our sequence. So there's definitely something wrong here, right? So let's just get rid of this arrow. Well, we need to come up with a new state, obviously. So what I'm going to do is I'm going to call this new state 1 0 ... 0, and here I'm going to write any number of zeros. You can call these states whatever you want, right? And we're going to get here just by getting a 0, right? And we're going to stay here if we keep getting zeros. So this is perfect, right? This is exactly what we wanted. Okay. Now what we really want is we want to get a 1, right? We want to get a 1, and that means that we're done. We've seen the pattern, and we're done. So at this point, if I get a 1, where should I go? Should I go to a new state called done or something and output 1? Well, that's a possibility, right? I could do that. But I also noticed that if I get a 1, like if I have a pattern like this, 1 0 1 0 1, this 1 in the center acts as sort of a 1 in both this pattern and this pattern. And both of those patterns output 1 once. So by getting 1, we're not sort of confining ourselves to being done or being at the end. We also could be starting a new pattern. And what state starts a new pattern? It's this one, right? This is where our start vertex, like we said, like this was the loser vertex where we ended up if we got horrible inputs that didn't get us anywhere. And this was the vertex that lets us start seeing a new pattern. So in this case, while this would work technically, it's easier to just take this state, take it back to 1 with a 1 1. And that means that this path is sort of taken on once you see a bit like this. That it means you finished one pattern, but you could be starting another one with the same last bit, which is pretty cool. Okay, so let's just quickly look over our FSM to see if we have satisfied 2 edges coming out of each input. So there's 2, out of each vertex. There's 2 out of the start, so that's good. There's 2 out of 0, so that's good. There's 1 coming out of 1, right? So that's kind of bad. We need to fix that. And there's 2 coming out of this giant ugly vertex I made. So that's fine, right? So what are we missing here? We have an outgoing edge from 1 if there's a 0, but if there's another 1, what should we do? Well, if we get 1 1 like that, we should just go back to where we were, because we could still get another pattern, right? These 2 1s both mean we could be starting a pattern. So in this case, if we get a 1, we should just go back. And that's the end of our FSM. So, congratulations, me. Cool. Let's talk about pipelining. So, we were talking about the data path before, and now we get to figure out what the pipeline stages are. So, the pipeline stages are as follows. Instruction fetch. This is where we fetch the instruction. Instruction decode. This is where we take the instruction and we figure out the registers, what the instruction is doing. We go in the reg file and get the contents of the registers. We figure out the immediate generator. So a lot of stuff is being done in this stage. Okay. The next stage is the execute stage, where the ALU executes the instruction. Also, there's a branch comparator that does figures out which branch to take, or if you want to take a branch or not, if it's a branch instruction. Right. After the execute stage, you have the memory stage. This is used in like load word or store word to access memory. And then finally, at the very end, you have the write back stage. And the write back stage is where you write back to the register file. So these stages are not really that well drawn on this diagram. So basically, the instruction fetch stage looks kind of like this. You have the it's basically just the instruction memory over here. Okay, the instruction decode stage is also just this. So it's the register file and the immediate generator. Notice how I drew this little thing around the write back, because that's part of the write back stage. Even though the write back stage is over here, it goes all the way back over here. So that's why I was saying that these are not the most well drawn things on this diagram. Okay, so the execute phase, all right, is over here, and it includes both of these muxes and this branch comparator and the ALU. Okay, but that's not all, which is really interesting, because after the ALU, you can see that actually this is when the PC is set, because the PC is sort of just waiting on the ALU. So the execute stage actually includes all of this. Right, which is why sometimes you'll see that there's an extra mux in the operations to calculate the critical path of the execute section, which is this mux over here. Okay. Now there's the memory section. The memory section is pretty straightforward. It includes this memory and this mux, and also I guess this +4, but that's never really used any calculations. And the write back stage is just this really long snaky stage that goes back here, and it basically just includes this right here. You're just writing back to the register file. So that's the 5 stages right there. Kind of weird, but that's what they are. If you're more interested in what these stages actually do, the previous discussion 7, has descriptions in the solutions of what the 5 stages do. So you can take a look at that. Okay. So this discussion is asking, what's the purpose of all these registers? So the register's purpose is that they're there to pipeline the data path. That's what we mean by pipelining the data path. The registers allow each stage to have a set of values for its corresponding instruction, right? So that means that because there's an RS1 stored here that might be different from what's being read over here, we can have 5 instructions being executed at the same time in this data path, which is really cool. So the purpose of the registers is that this is how we pipeline. Each instruction has different values and also control signals. You can't forget control signals. I mean, how could anybody forget after Project 3? Okay. 2.2 says, why do we add +4 again to the PC in the memory stage? So that's what I was looking at earlier. Right here in the memory stage, we add PC +4 again in order to have PC +4 in the mux. Now, why didn't we just take PC +4, which is conveniently calculated for us over here, and just take it and shove it in over here? Why do we do the extra +4? Well, it's because right now we're already passing PC in all these registers, right? There's PC here, there's PC here, there's PC there. And if we pass PC and PC +4, we would need 2 registers. So we need 2 registers side by side here. And it turns out registers are a lot more expensive than just adding this, right? Because this is just an adder, right? It's very, very cheap. And it's not even like a fancy adder. It's an adder that just adds 4. Okay. So the answer is we don't want to store PC and PC +4 in registers. This is expensive. 2.3 says, why do we need to save instructions in registers multiple times? The answer to this is pretty much the same as in 2.1. Why do we have these registers in the first place? We specifically care about our control signals in this question, so each instruction needs to have the right control signals. That's the answer. Otherwise, you would execute the wrong instructions, right? We need to make sure that we're keeping track of what instructions are being executed where. And that's why we need all these registers to store everything. So we can store the contents of not just one instruction, but 5 on this data path, which actually is a lot of work. Cool. Let's talk a little bit about performance. So performance, we're just talking about the time it takes, the critical path time for both a non-pipelined and a pipelined data path. So we've seen this formula before. It's the minimum clock cycle time formula or critical path formula. And what we've seen this before is in circuits, but if you think of the data path is a circuit, so this is definitely applicable for the data path as well. And what this formula says is the minimum clock cycle time, or the critical path of the circuit, is equal to the clock to queue time of the starting register added to the longest combinational logic time in our circuit between 2 registers, or between an input and a register, or between a register and an output, or between an input and an output, right? We're not that picky. And add this to the setup time of the destination register. So we're going to be using this formula a lot in this section. So the first section tells you that the register clock to queue time is 30 picoseconds, and the branch comparator is 75 picoseconds, and the memory write is 200 picoseconds, and all these other things about how long each part of the data path takes. And then it asks you, what will be the fastest possible clock time for a single cycle data path? Well, the fastest clock time is just the smallest clock cycle, and so we just need to calculate our critical path. So our critical path is usually a load word instruction or something, because that usually will take up every single part of the data path, because a load word not only reads from memory but also writes to a register, so it uses up all 5 sections, which is really cool. Almost no instructions do that. I think load word is actually the only one. So well, actually also load byte and load whatever, but that's the same thing. So let's find the critical path. So this is equal to the time for clock to queue plus the longest combinational logic time. So let's go find that. The longest combinational logic time, right? We start here, right? We have the clock to queue from the PC, and we go through our instruction fetch, right? So we need to go through the IMEM, and then after the IMEM, we go through the register file. We read something from the register file. At the same time, we generate an immediate. So we generate an immediate and look in the register file at the same time because they're in the same section. Now, after the register file read, we go through these 2 muxes at the same time. There's 2 muxes we go through at the same time. And at the same time as those, we go through the branch comparator. So we're going through all this stuff at the same time. The branch comparator doesn't actually happen for load word, so we don't really need to worry about it, but in this example, the branch comparator is 75 picoseconds anyway, which is a lot less than the ALU time, which is 200 picoseconds. So there's no way this would ever be the critical path anyway. So we don't really have to worry about it, at least for these values, for how long everything takes. Okay, now we go through the ALU. The ALU takes up some time, and then after that, we have to go through memory to load, because we are doing load word. We go through this mux, right? And then we finally write back to our reg file. So that's how long our critical path is for load word. We have to go through all of this crap, basically. It takes a really long time. So let's calculate this up, right? So we said go through the clock to queue, then go through the IMEM. So read the IMEM. Then after that, read from the register file, right? We got to read our registers. That's happening at the same time as the immediate generator. But the immediate generator apparently takes 0 picoseconds because it's not even included. So we don't really care in this example. Then we go through the mux. This is the mux right before the ALU. There's two muxes, but we can just say they happen at the same time. And the branch comparator happens at the same time. Then we go through the ALU. Then we go through the DMEM read, right? Because we're going to be loading something. Then we go through the mux, that's after the memory, that tells you what to write back. And then we're done, right? But we do have to add the setup time of the destination register. The destination register in this case is the register file, so we will add the register file setup time. Okay. And what this comes out to is 30 plus 250 plus 150 plus 25 plus 200 plus 250 plus 25 plus 20. And it equals 950 picoseconds. Saved you a calculation. We aren't being asked for the fastest clock time, so we don't need to calculate the frequency. But if you want to calculate the frequency, you could just do 1 divided by 950 picoseconds, and you get around 1.05 gigahertz as your frequency. Okay, cool. Let's talk about a pipeline data path, because that's significantly more interesting. So for a pipeline data path, you now have to clock to the whatever stage is hogging up as much time, because that stage is going to take up that much time every single clock cycle. So every other stage is going to suffer as a result. But to figure out what stage it is that's hogging up all the time, we need to calculate the critical path for every single stage. And notice how now there is a critical path for every single stage. Before we said we started out here and we went all the way through the entire data path until we ended up with a reg file, right? So that was our register to register path. Our first register was here at the PC, and our final register was here at the register file. So that was our critical path. And now we have added all of these registers. We've added this line of registers here. We've added this line of registers here. We've added another line of registers here, right, etc. And that allows us a lot more registers to have critical paths in. So it's now a lot more interesting. So for our instruction fetch, we see that our critical path, first we have a clock to queue, right? Our instruction fetch starts with a PC, just like before. So we start off here, and we have a clock to queue, and then we go into the instruction memory, and then we write to a register immediately. That's our entire instruction fetch. So it's the time to clock to queue, it's the time to read from our instruction memory, and it's the time to set up a register, not a register file, right? So this is just a regular old register. Okay. What about instruction decode? The instruction decode says read from this register, right? So that's our clock to queue from this register now. Go into the register file, okay, do something. At the same time, do something in the immediate generator. Then write something to this register. Okay. So we know in this example our immediate generator takes up 0 time for some reason. So all we'll really care about is the clock to queue from a register, doing some sort of reg file read, and then setting up a register. Cool. Execute. So I'm sure this is getting familiar for everyone. Execute, you read from a register. Wow, go figure. You'll branch comparator at the same time you'll mux an ALU, right? Oh shoot, I did not mean to do that. Okay, so after you mux an ALU, you'll write to another register. So what this is the time for a clock to queue, plus the time for that first mux, plus the time for the ALU, plus the time to set up the register, and remember this, right? Remember this over here. This is important as well. We need to write the ALU to this mux. So that mux time is going to be included at the end. It's a little straggler. Okay, so that's our execute phase. Next is the memory phase. So the memory phase, we said, okay, read from a register, read something from memory. Remember, we're reading from memory because this is load word. Then we go through the mux, and then we write to this register over here. So that's what we're going to do. So we need the time for the clock to queue. We need the time to read from memory. We need the time for the mux. And then we need the time to write to a register. So this is a register setup. Okay, and finally, the write back phase. Right, the write back phase, we just read from this register and then we write to the register file. So that's no big deal. Now we do a reg file setup instead of a register setup. Okay, so what takes the longest amount of time? Well, I'll save you the calculation. This takes 300 picoseconds. The next one takes 200 picoseconds. The next one takes 300 picoseconds. The next one takes 325 picoseconds. And finally, the write back takes a measly 50 picoseconds. So clearly that one's not doing a critical path. The memory wins. So memory is the time hog. And so our fastest possible clock time is 325 picoseconds. So now we're asked in 3.3, what is our speed up? So I'm sure everybody after that horrible homework assignment is used to calculating your speed up. You just divide your slower time by your faster time. So our old time from part 3.1 was 950 picoseconds. So we sped it up to 325 picoseconds. So our speed up is 950 over 325. And this is around a 2.9x speed up, which is not bad. It's not a 5x speed up, right? We pipeline into 5 parts, so you might think we have a 5 times speed up, but there's a lot of overhead. And overhead is caused from registers, so we keep writing to these registers and reading from these registers. There's setup and clock to queue times. It takes forever, right? So that's already going to take us down. The other thing is that our data path stages are pretty uneven. The write back is only 50 picoseconds, but it still has to wait 325, right? So if every single data path stage took the exact same amount of time and there was no registers in the middle, then we would have a 5 times speed up. But that would be a more perfect world than the one we live in, and so we have to just deal with what we have, or something like that, right? Something to be said about living plainly, like the Buddha would have wanted. A forest. You could be reincarnated as a beautiful flower one day, or a butterfly. Okay, cool. So, part 4 is about hazards. So, there are 3 types of hazards we really care about. The first one is a structural hazard, and the second one is a data hazard, and the third one is a control hazard. So I'll talk about each one. So structural hazards occur when more than one instruction needs to use the data path, a data path resource at the same time. The 2 most common ones we see, both occur in the reg file. So a lot of the time, a reg file is being accessed during instruction decode, but then is accessed again during write back. And if we have both of these as stages in our data path, that means two instructions are trying to access the register file at the same time. Mostly we just fix this by having two ports. One is for writing and one is for reading. So you see that in the picture there is a write port and a read port. So this is not too big a deal. A lot of the time we can also solve another problem which is related, which is that sometimes the writing register and the reading register are the same register. And you can't really access two registers in the same clock cycle with two instructions. I mean, two of the same register, right? But you can with this thing called double pumping. So double pumping says, why don't we just allow instruction 1 to write to the register in the first half of the clock cycle and allow instruction 2 to read from the register in the second half of the clock cycle. So this is a brilliant idea. We'll just divide the work in half, I guess, or the amount of time each instruction has in half. So this says that we can read and write in the same clock cycle. So how we usually represent this is we'll have some instruction writing to the reg file, and it'll look like this. And then we'll have another instruction reading to the reg file, and it'll look like this. And as you can see, the read happens in the second half, and the write happens in the first half. We also have problems with our memory, but usually we just have two memories, an instruction memory and a data memory. They're in fact the same memory, but we use some fancy tricks to make it look like they aren't, and this fixes a lot of issues. So structural hazards are, kind of annoying, but you can always just fix them by buying more hardware. So if you have infinite money, you will never have a structural hazard. Yeah, just buy another register file. Think about that, right? Like, forget double pumping, just have two. And then actually in modern processors, sometimes they'll just have the entire processor copied and pasted again. So after this 18-stage pipeline or whatever they're doing in Intel's processors, they'll just have another one. And if you buy an Intel processor these days, you'll have 4 or 8 cores on your processor, which is like, yo dog, I heard you like processors, so I got you another processor on your processor. Yeah, it's always funny. Ha ha ha, a little bit of humor in your 621C discussion. Okay, so the second type of hazard I want to talk about is a data hazard. And data hazards, there's a lot of different types, but the general idea of a data hazard is that there's data dependencies between some instructions, and usually instruction B is reading something, a register, but instruction A was supposed to write to it like one instruction beforehand, and it wasn't able to because of how the instructions were set up. It wasn't able to do it in time. So instruction B reads a register before instruction A can even write to it. So how do we fix this? Well, we have two really clever ways to fix this. The first, maybe not even that clever, it's actually kind of stupid. The first is called stalling. And stalling just says, just wait until instruction B writes. Or sorry, instruction A writes. Okay, well, this fixes everything, because instruction B says, oh, I don't have the right data yet, let me just wait until it shows up. And it works, but it's super slow, so it's kind of stupid. So that's why we have another smarter idea called forwarding, which states that, well, there's no reason to wait for all of instruction A to write. Instruction A has calculated the value once it's done with the ALU. So why do we wait for it to write to the register? Well, we can just tell instruction A, because all the instructions are friends here. They go to each other's kids' birthday parties and have barbecues. So instruction B goes into instruction A and just says, just give it to me from your execute phase, and I'll take it early. And so that's what happens. So we'll just send from an earlier data path stage of A before we're finished writing to a register. Cool. So let's see an example. Okay, let's get started. I want to forward instructions in order to fix the hazards in this set of instructions. So let's take a look at what my hazards are, right? So first I notice that in instruction 1, T0 is updated, but T0 is used in instruction 2, so that's a hazard, right? And also T0 is also used in instruction 3, so that's another hazard, because when is T0 finally updated? Well, T0 is finally updated here, right, in C6. After the entirety of instruction 1 is executed, then T0 is finally updated here in C6. But T0 is read here, right, in C3, because the instruction decode phase reads the register. So we need to somehow get the value from here all the way back here. Well, that's impossible. It's going backwards. But we can do something almost like that, because we don't really need the value in instruction decode. That's where the value is read, right, in a normal instruction. But what the instruction really needs the value in is X. It needs the value of T0 for the ALU operation. So we can forward the value from this previous X over here, right here to this X. And that actually solves our data dependency, because now the value of T0 after it's been updated, which happens here, right, is now going into X right here before it's being used. So this is perfect, and it allows us to forward to fixed data dependencies. We also notice that T0 is required here at this X as well for instruction 3. But this isn't a problem either, because we can also just forward the value over here as well, allowing us to fix both of these data dependencies. So now we're asked, what would happen if we didn't have forwarding? The question specifically asks, how many instructions after the add-I instruction could be affected by data hazard? So if we didn't have forwarding, how many stalls would we need, for example? Well, in truth, the amount of instructions you need is just until the instruction decode can read the finished T0 over here at C6. So we'll have a fourth instruction here. It doesn't matter what it is, right? It'll start here, IF, ID, X, mem, and WB. And we'll have a fifth instruction here, IF, ID, X, mem, WB. And we'll notice that T0 finally gets its updated value here at C6. So anything that has an ID at C6 or later will be able to have the updated T0, which means that 5 is the very first instruction where we actually have the right value for T0 to go into the instruction decode phase. So at most, the CPU data hazard can affect 3 instructions. Of course, it could affect less than 3 instructions if they didn't actually require T0. Now, if we use the double pumping that we were talking about earlier, it's possible that we can write on the first half of C5 here, and then read on the second half of C5, meaning that now we only affect 2 instructions, because the third instruction, or after 1, which is the fourth instruction, is able to read the value, is able to read the register that's been updated. Now let's talk about stalls. So in this code, we're asked to forward again. So let's look for data dependencies. So the first thing we'll do is we'll look here. Okay, S0 is being updated with the previous value of S0. And here, T0, T04, right? T0 is being updated, but nothing happens with S0. So there's no dependencies yet, right? Now, here's a dependency, right here. That's a dependency. So this T0 and that T0, right? The load word requires the updated value of T0, but it's not updated until instruction 2 is done. So that's definitely a problem. And for number 4, we need T1. But T1 is updated in instruction. So the value of T0 is needed for part 3, right? And we know that it comes out of the execute phase in part 2, because that's when it gets added. And what phase is it needed in? Well, it's needed in the execute phase for part 3, right? Because it gets added to 0, and that's what you load from that memory address. Okay, now let's try to deal with the T1 problem. Okay, so T1 is required in part 4's execute phase, right? In instruction 4's execute phase. But we can't forward it from part 3's execute phase. And the reason why is because T1 is not updated until after we access memory, right? So this isn't an add instruction, this is a load word. So we need to wait until we access memory in order to get the value of T1. So let's look in memory here, but we can't forward in the same clock cycle, right? That's not allowed. And that's why we need to stall in this case. When you can't forward down or backwards, you can only forward to the right. So let's stall instruction 4 by getting rid of this instruction entirely and just writing instruction 4 as a no-op. A no-op is just an instruction that doesn't do anything. So an example is 0x13 from your project, which is add I x0, x00. So now we've stalled, we're going to add a 5th instruction, which was our original add instruction. And now, as you see, it's later. It's 1 clock cycle later. And so now we can actually forward, because now we need to take mem into the execute phase, and we'll just do that. So we can fix this with 1 forward, which is pretty cool. We just need to stall 1. A lot of modern compilers are able to reorder instructions in order to minimize data hazards like this. So if we were some kind of compiler, we could maybe just insert instruction 2 as instruction 4, and that way we would get rid of the hazard. And if you look at it really hard, you'll be able to see why. Finally, I want to talk a little bit about control hazards. So control hazards are caused by jump instructions and branch instructions. So control hazard caused by jumps and branches. And this happens when a jump or a branch could execute a different instruction than the one that you're expecting. So we sort of expect that the next instruction will always be at PC plus 4, but the jump or branch will take us to a whole another section of code sometimes. So in that case, we'll execute the wrong instruction entirely. And this is kind of a problem because you might not even know where you're branching to until the instruction is done executing, for example. And the next instruction, you don't want to just stall 4 times after every single branch or jump, right? But you can. That's a way you can fix these hazards, but it takes a long time. So another way you can resolve a control hazard is with a branch predictor. And a branch predictor just guesses which branch you're going to take. So you can solve this with a branch predictor or by stalling. With a branch predictor, there are problems where you could guess the wrong branch, and that actually happens quite a bit. And in that case, you will need to flush the whole pipeline, which means you need to replace everything in the pipeline with no-ops. Branch predicting can also cause some security vulnerabilities. There's a really interesting one called Spectre, which involves a side channel attack. It involves, well, anyway, you can read about that. It's not really like important for this class or anything. Okay, so there's another one called Extra for experience, but I'm not going to do it. You can do it on your own for experience. And yeah, so thank you for watching.